have been able or have come across a magnet. Niko sure mshaipatana na magnet mahali. And if you have ever been curious of how a magnet works, today we are going to discuss in details some of the theories or some of the things that are behind a magnet. Now, we are going to start with terminologies that we'll encounter when we talk about magnetism and electromagnetism. So it is good tuweze kuzijua sasa hivi so that when we continue with this topic, we will not get hatutasahau ama tutapotea. The first one is magnetic flux. When you talk about magnetic flux, when you represent a magnetic field katika diagram, kuna ile mfano kidogo tu. When we represent a magnetic field in a diagram, what tunaichora namna hii. We have these lines. And these lines are what we call magnetic flux. They're those lines that we use to represent a magnetic field, usually produced by a magnetic source. Now, when you represent magnetic flux, for example, in an equation or in a formula, we use this symbol. This symbol inaitwa phi, phi, phi. And the unit of measurement, the way you have the unit of kilograms for mass, seconds for time, for flux, the unit of measurement is Weber, usually abbreviated as WB. Magnetic flux is the amount of field, the number of lines produced by a magnetic source. Its symbol is phi, and the unit of measurement is Weber. Now, magnetic flux density. This is usually the amount of lines, the number of lines ambazo zinapita in a defined area that is perpendicular to their direction. The amount of lines, zile numbers are those lines that are produced by a magnetic source. When they pass through an area that is perpendicular to that direction, that is what we call magnetic flux density. Its symbol is B. It's beta. Let me call it beta, not B. But symbol yake ndio hiyo hapo. When you see it in an equation, you'll know that is magnetic flux density. And its unit of measurement ni Tesla, usually abbreviated as T. Are we together? Now, let us try this example. These are the types of questions ambazo utapatana nazo kwa mtihani. You're told that a magnetic pole has a rectangular section having dimensions of 200 by 200. If the total flux, the number of lines, imagine from the pole, ni 150 microweber. Calculate the flux density. We have been given the cross-sectional area, the dimensions, so it is very possible to if you have a place that you can do this calculation, please do so. Kama unaweza pia I want us to do this example together. You can see my screen. Can you see it? Now, we've been told that a magnetic pole has a rectangular section. And its dimension is, let's say for example, this is a bar magnet. This is our north, this is our south. We're told that the cross-sectional dimension is 200 millimeters. And we've been told that 200 by 100 millimeters. Now, we've been told that the total flux, the total number of lines being emitted from this pole is 150 microweber, meaning that it is 150 times 10 raised to power negative 6 Weber. We have been told to calculate the flux density. We had seen that in our magnetic flux density is given by beta or B is equals to flux or the number of lines being emitted from the magnetic source divided by the cross-sectional area. We have been given the value of flux as 150 times 10 raised to power negative 6 Weber. Area, we have the cross-sectional dimension, so it is very possible to calculate the area, and we've been told that it's a rectangular cross-section, so meaning that the area will be given by length times width. But now the area, the dimensions are in millimeters, so we have to change those dimensions to be in the base units, which is meters. So area is 0.2 meters times 0.1 meters. So what will be our area? What will be our area? We have to do calculations together, so please, area yetu itakuwa ngapi? .2 times 0.1. Our area will be 0.2 meters squared. Now, flux density, therefore, will be given by 150 times 10 raised to power negative 6, or you can say 150 divided by a million. This micro is just divided by 1 million. Now represent it, when you represent it in scientific form or standard form, in the way up. So flux density B is given by the flux, magnetic flux, which is we have already been given, divided by the area, which is 0.02. So ukifanya your calculation, 150 times 10 raised to power negative 6 divided by 0.02. You get that your flux density. Your flux density is 7.5 times 10 raised to power negative 3 Weber. No, let me say Tesla. Are we together? Are we together? Are we together? Am I speaking to someone? Tuko pamoja? Okay. Is there any question up to that point? Okay, I'm assuming there is no question. Now, let us go back to our slide so that we can continue. Now, those are the types of questions that you'll get in the exam. You'll be given dimensions, or you'll be given those types of questions. All you have to do is apply the formula, replace those values in the formula. I have another example over here, but I will leave that as kama homework. Mwende mjaribu so that you can see whether you can be able to apply that formula, magnetic flux density. Now, magnetomotive force, MMF. This is a force that causes, or that makes the magnetic field, causes the existence of a magnetic flux. The same way in an electric circuit, we have electromotive force, some voltage that causes the flow of current in an electric circuit. In a magnetic circuit, the similar force is there, ambayo inaitwa magnetomotive force, MMF, that causes the existence of magnetic flux. Hiyo ndio inasukuma the flux within that magnetic circuit. And it is given by Ni, N being the number of turns, or the number of conductors in that magnetic circuit, multiplied by the current flowing in that magnetic circuit. We will see this sana when we talk about electromagnetism, where we have a conductor, a conductor that has been coiled, that has been imekunjwa, and we have coils. We will see that later on when we talk about electromagnetism. Something else that I want to introduce is magnetic field strength, magnetizing force. This is the driving force of those of that of that flux. Yeah, the magnetic MMF enables the magnetic field, the magnetic lines to exist. But the magnetizing force is what enables that magnetic flux to move within that magnetic material, that magnet, and it is given by the Ni. It's usually represented by letter H, but it is usually given by Ni divided by L, and its unit of measurement in ampere per meter, where L is the length of the flux. Ile njia ambayo that flux is using in meters. I want you to look at something over here. We had said that this magnetic force is given by N times I. H, which is the magnetizing force, is given by Ni times L. When we make this Ni the subject, we'll get that HL is equals to Ni. Therefore, we can say that the MMF, magnetomotive force, is equals to Ni. It is also equal to HL. We have just removed the L from the denominator and multiplied by H. So you can, if you're given a question and you're told to find MMF and you have been given the value of H and you have been given the value of L, you can still find the answer. Sio lazima ukuwe tuna value of conductors and current. You can have the value of H and L and you will still find MMF. We will see this in an example. Now, let us try this example. Let us try this example. You can be writing it down mahali. Now, we have been told that a magnetizing force of 8,000 amperes per meter is applied to a circular magnetic circuit of mean diameter. So we have a magnetic circuit that has a diameter of 30 centimeters by passing a current through a coil wound on the circuit. If the coil is uniformly wound around the circuit and has turns N, 750 turns, we're told to find the current in that coil. So, magnetizing force H, tumepatia that it is 8,000 amperes per meter, and it is applied in a circular magnetic circuit of mean diameter of 30 centimeters. A magnetic circuit, let's say a solenoid. An electromagnet. You have a conductor which is wound into coils and you connect it to a source, a voltage source. So the force that will drive the magnetism in that circuit and is given as 8,000. And we are told that the mean diameter of this circuit is 30 centimeters. By passing a current through the coil wound on the circuit. If the coil is uniformly wound around a circuit and has 750, so these turns are 750. So find the current in the coil. Is there anyone who can try to do that question before we continue? Let me present that question again for those who are not able to write it down. Kuna mtu ambaye anaweza jaribu kufanya that example. I'll give you a minute down to note the question down for those who did not. Can I continue? Naweza endelea? Has everyone been able to write the question down? Okay. When I do the calculation, is it clear? Mnaweza ona? Okay. When you're ready to continue, please let me know. Let us continue. Kwa sababu I will still send this presentation to you. Wacha tuendelee so that we don't end up taking a lot of time. Now, the question is telling us to find the current flowing through that magnetic circuit. Now, we know that magnetizing force, H, is given by N, the number of turns, times the current flowing in that circuit, divided by the mean length, L, that the flux is using, the length of that flux, the lines. If you look in this question, we have the value of H, which is 8,000 amperes per meter. We have the value of N, which is 750. We do not have the value of I, the current. That is what you are looking for. And we also do not have the value of the length. But we can get the value of the length. How? We have been given the diameter. We are told that this magnetic circuit, the flux zitakuwa zinazunguka hivi. So what we want to find is the mean length. So how do we find the length? How will we find the length of these magnetic lines in a circular circuit? We have been given diameter. We have been told that these lines, the magnetic lines, follow a circular magnetic circuit. So how will we find the length that these lines follow? Anyone? You have a circle. How will we find the length, E length? Yes, we will find the perimeter. Now, do we find the perimeter of a circle? The perimeter of a circle is pi d. We have the diameter, which is 30 centimeters. So we have to change it to meters. So pi times 0.3 to get the length that this magnetic field, the magnetic lines will follow. So pi we'll get that the length of that magnetic circuit is 0.9425 meters. Sawa. Now, in this formula, let us replace the values that we have. H is 8,000, is equals to N, the number of turns is 750, times I, which we do not know, all over the length, which is 0.9425. So let us make I the subject. I will be equal to, we take 8,000, we multiply by 0.9425, we divide by 750. So 8,000 times 0.9425 divided by 750. So what will be the current in that magnetic circuit? 10.053 amperes. Are we together? Are we together? So in these questions, all you have to find out is what you have and what you don't have. Okay? And then you replace the values that you get in your equations, the equations that we are talking about right now. Now let us continue. The next thing I want to talk about is permeability. Now, permeability is the ability of a material when you expose it to a magnetic field, and the magnetism ambayo that material will obtain by exposing it to a magnetic field is what we call permeability. Are we together? Magnetic permeability is a measure of magnetization that a material will obtain when you expose it to a magnetic field. Now, this permeability is usually a constant. It is a constant that is a ratio of magnetic flux density beta divided by magnetizing force H. Now, this constant is usually this value ambayo mnaona hapa inaitwa mu. Sio u, ni mu. So this constant is mu, and it is known as the permeability of free space. And it is already being given a value which is 4 pi times 10 raised to power negative 7 Henry, ama H per meter. This is mu, permeability of free space. This is usually for air and non-magnetic mediums. Are we together? This permeability, the permeability of free space is usually 4 pi times 10 raised to power negative 7. It has already been given. It is a constant. Now, for other mediums ambazo that are not air or non-magnetic materials, those that have magnetism, we get that the ratio, that permeability, B over H, is usually given by that permeability of free space multiplied by something we will a new term, which is this mu r, which is known as relative permeability. For other medium that is not air, free space or a magnetic material, the permeability B over H is given by this, which we have called it the permeability of free space times this value, which is known as relative permeability. Are we together? Are we together? Wapi hapo? Kuna B over H is equals to EU. Unasema hii zero? Let me see if I can expand. Umeona sasa? Yeah, so for other mediums that are not free space, we get that the permeability is given by this value, which you have called it the permeability of free space, which has a constant. It is a figure that has already been given, multiplied by another new term, which is known as relative permeability, which is denoted by mu subscript r, where this relative permeability is the ratio of flux density in a material, sana sana magnetic materials, divided by the flux density in a vacuum. And the flux density in a vacuum sana sana is equal to 1. Now, this value, mu naught times mu r, is when we assign it a value mu, we call that absolute permeability. So this is relative permeability. This is permeability of free space, when you multiply these two, we get something known as absolute permeability. Are we together? Now, we said that this is usually a ratio. Permeability is a ratio of magnetic flux density, B, divided by H, magnetizing force. Now, when you get these values, labda umepatiwa swali na ukapatiwa the values of B and you're given the values of H. When you plot the values of B against the values of H, we get a curve known as the magnetizing curve. Magnetization curve or BH curve. Are we together? This curve inakam namna hii. This is usually for magnetic materials. For non-magnetic materials, it is just a straight line. The line too straight. But for magnetic materials, this indicates that, let's take for cast iron, or let's say for mild steel. Let's take mild steel. Mild steel, the magnetic properties of mild steel, when exposed to a magnetic field, will increase. The magnetism of mild steel will increase until it reaches a point where they will have something known as magnetic saturation. The magnetism itafika mahali even despite increasing the current, especially in electromagnetic circuits. To increase the current up to what point the magnetism of that material will not increase. So when you plot the flux density B against the magnetizing force H, what you get is a magnetization curve. There's a certain question like this in one of the NEC papers. You can look at it. You'll be given the values of B and the values of H, and then you're asked to plot. If it is a magnetic material, it will increase linearly until it gets to a point where itafika mwisho. And that place, mali itafika mwisho, is known as a point of magnetic saturation. Now, reluctance. Reluctance ni kama resistance in the electric circuit. This is the ability of a magnetic material, to resist the formation of magnetism in that material. That is what we call reluctance, and it is usually denoted by S. Now, the formula of reluctance is Fm, which was let me go back kwa sababu hiyo jina inanipotea. Magnetomotive force, MMF, which is denoted by Fm. Reluctance is MMF divided by flux, magnetic flux. And the formula magnetic MMF is N times I, the number of turns or the number of conductors multiplied by the current in that circuit, magnetic circuit, divided by flux. Remember that we had said that beta, which was magnetic flux density, is equals to flux divided by area. So what we've done is we've made the flux the subject. So you replace those values. So let me do it by hand so that we don't tusipote. Let me do that by hand so that we do not get lost. Now, reluctance S. Can you see? Mnaweza naandika whatever I'm writing. It is given by Fm all over flux. Fm, we had said that this is the MMF, magnetomotive force. Divided by magnetic flux. Magnetic flux, we had said, are the lines that are generated from a magnetic force, the number of magnetic lines generated from a magnetic force. This is equals to, MMF is usually given by Ni divided by flux. Ni, we said that N represents the number of turns or the number of conductors, and I is the current in that magnetic circuit. This is still the magnetic flux. This is equal to HL divided by BA. Remember, when we talked about tuanzie na hii ya juu, magnetizing force H. Magnetizing force H is given by Ni over L. So when we make Ni the subject, itakuwa Ni is equals to HL. Are we together? So what you have done in this equation this formula hapa juu is you have taken the value of Ni and we have replaced it with HL. Sawa sawa. Unaweza nisikia? Are you able to hear me? Naona napotea. Network yangu pia ina shida. Are you able to see my screen, whatever I'm writing? What can I do? If it is not clear, please niambieni ili nisikuwa naandika na muoni. Okay. Now, as I was saying, Ni, when we talk about magnetizing force H, it is equals to Ni over L. When we make NL the subject, so we say that NL is the same as HL. Ni is equals to HL. What we've done in this formula up here is we've taken the value of Ni and we've replaced it with HL. Are we together? Now, for flux, we had said that beta, which is the magnetic flux density, is given by the magnetic flux over area. So when we make the magnetic flux the subject, we'll see that magnetic flux is given by the magnetic flux density B times the area. So what we've done in this formula up here is that we have taken the magnetic flux and replaced it with B times A. Sawa sawa. Sawa. Network yangu ni mbaya sana. So I don't know if you're able to hear me or see what I'm writing. Are you able to see what I'm writing? You're seeing? Okay. Now, let us continue in a formula. So what we'll do in this formula is we'll divide the numerator by H. Okay? So we'll hapa juu tutabaki and the denominator by H. So we'll be left with L all over B over H times A. We've just divided the numerator with H and the denominator with H. Tunabaki na L over B over H times A. When you go back kidogo, tulisema that B over H for a magnetic material is given by the permeability of free space multiplied by the relative permeability. This is a formula for magnetic material. This permeability for magnetic material is permeability of free space mu naught times the relative permeability. So when you replace this value, mu times mu r easy hapa, what you're left with is L over mu naught times mu r times A. Are we together? This is the formula that we'll be using for reluctance. I was just explaining so that in case you find these other formulas mahali, usishangae zimetoka wapi. But the formula ambayo we'll be using majorly ni hii ya mwisho. S, reluctance, is given by L all over mu naught times mu R times the area. Are we together? Tuko sawa? I don't know if you're together, but I hope you're together. If you're together, please unmute and say present. Nisikuwa naongea peke yangu. Please, as we continue discussing, msinyamaze sana. Naweza pata naongea peke yangu bana. Now, the unit reluctance is 1/h, or area divided by Weber. That is the unit. There we have the unit of length is meters. The unit of reluctance is easy hapa mbili. You can use either. Now, let us look at an example and see whether we can be able to tackle it. I will give you a minute to write down that example so that we can be able to do it. Is there any question up to that point? Kuna swali? Kuna swali? Mna swali ama hamna? What I'll do is once I'm done preparing this presentation, I will send it to the class. I'm sure some of you may join like Google Classroom. That is why I will be posting these materials, because I can't send them using WhatsApp. They are too big. Mtakuwa nazituma hapo so that you can find them there. Hata sasa I'm recording this class. I started recording it from the beginning, so I will edit it. Nita-edit kidogo, kisha nitawatumia, so those who missed class ama those who could not attend this class are able to revise. Wasiachwe nyuma sana. Now let us calculate this question. If you have a place to write, please do. Now, we have been told that a piece of metal, its length is 150 meters. 150 millimeters. And it has a cross-sectional area of 1,800 millimeters squared. The relative permeability, mu r, is 4,000 Henry per meter. We are told to determine the reluctance S, and we are also told to determine the absolute permeability. Now let us start with reluctance S. We say that the reluctance is given by the length divided by the permeability of free space, mu naught, times the relative permeability, mu r, times the area. Are we together? In this formula, let us look at what we have. We have the length, we have the permeability of relative, we have the relative permeability, and we have the area. We also have this permeability of free space. I said that permeability of free space is usually a constant, and it is 4 pi times 10 raised to power negative 7 Henry per meter, h per meter. Are we together? Are you able to see my screen? Okay. Now let us replace the values you have. So we have to change these values at ambazo ziko in millimeters to meters, to their base units. So the length will be 0.15 meters. Changing millimeter squared to meter squared is you will divide by 1,000,000. So itakuwa 1,800 divided by 1,000,000. What do you get? Hmm? 1.8 times 10 raised to power negative 3 meters per meter squared. Now let us replace those values in that equation. So S is equals to, our L is 0.15 meters. Ya nani? Amuoni kabisa. Let me are you able to see now? Okay. Now let us replace the values that we have katika hii formula yetu. S is equals to L. L is 0.15 meters divided by mu naught. We've said that mu naught is a constant and it is 4 pi times 10 raised to negative 7. So mu r, we have been given mu r as 4,000 times 4,000 multiplied by area. Area we had been given in millimeters squared, but we changed it to meters squared. So times 1.8 times 10 raised to power negative 3. What will be the value of reluctance S? S itakuwa ngapi? I want someone to give me the answer. So that I can see whether we are on the same page. What is the value of S? Two point? Times 10. 2.7 times 10. 2.7 times 10. Negative. Eight. Are you sure? Kuna mtu mwingine akona different answer? Negative 8. Is there another answer? Am I in the final answer? Is there a final answer? Kila mtu amepata hiyo answer? Now let us do it together. We start calculating the bottom, the denominator. So we have 4 times pi times 10 raised to negative 7. 4 pi. Iko. Pi is, you get pi by kufinya shift by hii hapa exp. Ukifinya shift na exp you'll get pi. I don't know if you can see. Nadhani nikishika screen yangu imehang ama network leo imekuwa mbaya sana. Let me see whether Can you see now? Yeah? So ni shift na hii hapa. That will give you pi. Yeah, so it is 4 times pi times 10 raised to negative 7 times 4000. Times 1.8 times 10 raised to negative 3. And then 0.15 divided by the denominator. That is the answer. Sawa. The answer is 1657 8.64 per Henry, or area per Weber. You can use either of the two units, but that is the value of the reluctance. Sawa. Now the second part of the question ilikuwa inauliza you find the absolute permeability. Absolute permeability mu is equals to mu naught times mu r. You take the permeability of free space, you multiply by the relative permeability. We already have those two values. So ni 4 pi times 10 raised to negative 7 multiplied by 4000. So what will be our absolute permeability? 4 pi times 10 raised to power negative 7 multiplied by 4000. What will be our absolute permeability? Anyone? What? Ni ngapi? $5.0265 times 10 raised to power negative 3. Are we together? Yeah, so that is the answer. That is the answer of the absolute permeability. 5.0265 times 10 raised to power negative 3. Now for today I'll have to stop there kwa sababu I have another class. But next week we will continue and look at types of magnetic materials. But there is something that I want to leave you as an assignment, ama homework. Nataka msome, and then when we come to the next class, you will explain to me what it is. I think I'd even given you katika in the assignment and the cut. It was in the cut that I'd sent you initially, ile ya kwanza. Na nimeona kuna watu wachache bana wametuma, kuna watu bado hawajanitumia hiyo cut. I'd asked you to explain to me what hysteresis is and how it affects magnetic materials. So next class ambayo tuko nayo on Tuesday, by the time tunafika, at least have an idea what hysteresis is and what hysteresis loss is when we talk about in terms of magnetism. Sawa. have an idea of what hysteresis is and hysteresis law, so that when you come to the next class, mtaniambia ni nini. I will ask questions for those who have attended today's class. But today I wanted to just introduce this topic. I'm sorry to hatungendelea mbali kwa sababu time is not on our side, but thank you so much for sacrificing. Naelewa mambo ya bundles it is an issue. So thank you for attending this class.